Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the next summary in the Padisco Introductory Statistics video series. In this one, we're going to be talking about comparing populations. In particular, we'll go over dealing with two population parameters, inferences about two population proportions, and inferences about two population means. We'll start by looking at when and how we deal with two population parameters. For the situations we've looked at thus far in this series, we've only ever looked at ones where there is one population parameter that we're trying to find out about. But many of the more interesting situations in statistics involve two or more unknown parameters. Suppose, for example, that the local council wants to build a footbridge somewhere in the city. It's wanted to build the bridge for some time actually, and it's a bit controversial because many residents are complaining about what the construction will do to surrounding houses. So 6 months ago, the council surveyed 1,000 people and found there was 65% support for the bridge back then. And today, they surveyed 1,000 people and found that there was 70% support for the bridge today. So it seems in the two surveys, the level of support has gone up. But has the level of support in the true underlying population gone up? Answering that question will involve making an inference about not one, but two parameters. The reason for this is that the council doesn't know the population proportion of people that support the bridge today. It only calculated a sample proportion. And similarly, it doesn't know the population proportion of support 6 months ago either. So there are two unknown parameters, and we now want to draw a conclusion about how those parameters compare. To be more precise, we want to draw a conclusion about the difference between these two population proportions. If we can conclude that difference is positive, for example, then we can say that the level of support has actually gone up. So how do we approach this new situation? Well, we'll start by looking at comparing two proportions. What we'll find is that we want to look at the difference between two sampling distributions. Remember when we were looking at one parameter, like a proportion, pi, or a mean, mu, we went to a sampling distribution, p, or x bar. Well, now we want to look at the difference between two proportions, pi1 and pi2. And so we'll need to use the difference between two sampling distributions of the proportion, p1 and p2. So now, just to be clear, let's be clear about exactly what situation we're in. We want to compare two population proportions from two different categorical populations. In the council survey, the council want to compare the current level of support for the bridge with the old level of support for the bridge. We collect a sample from each population, and this gives us two sample proportions. The council's survey today gave a sample proportion of 70% support. The old survey gave a sample proportion of 65% support. And the idea is that the difference between these two sample proportions, P1 minus P2, will be used as an estimate for pi1 minus pi2, just like we used P as an estimate for pi. So the fact that the level of support has gone up by 5% means that 5% is our estimate for the true difference between level of support today and level of support 6 months ago. Now, little p1 is a sample proportion from the distribution p1, and similarly little p2 comes from the distribution p2. So what sort of distribution is p1 minus p2? Well, using some of the theory from an earlier video, we can say that p1 minus p2 is approximately normal, with mean pi1 minus pi2 and standard deviation given here. And that is what is going to help us estimate or test pi1 minus pi2. Now, I should mention that it's assuming all of this that your two samples are collected independently. I'll be assuming that throughout this video. In the Padisco textbook, we do have a section on comparing two means when the samples aren't independent, so go there to have a read of that. But for now, the hard work is now done. Just as with one parameter, knowing about the sampling distribution actually tells you everything you need to know about any confidence interval or hypothesis test that you'd want to study. For example, we can say that the confidence interval for pi1 minus pi2 will have a centre of p1 minus p2 and a margin of error given here. Here are the numbers for the council surveys, and if we want to construct a 95% confidence interval, we can show that it's 0.9% up to 9.1%. That is, we're 95% confident that the level of support for the bridge has improved by somewhere between 0.9 and 9.1%. We could also look at testing the difference between two proportions, but I'll move along now to comparing two means. And the interesting thing about comparing two means is that, similarly to when we were looking at just one population mean, our method is going to depend on whether the two standard deviations of the two underlying populations are known. Now, there are actually three separate cases. Either we assume that they're both known, or we don't assume that they're both known, that's actually the most realistic option, or we don't assume they're known, but we do assume that they're equal. So for pretty much the rest of this video, I'll be talking about those three cases. The important point is that actually the general method of comparing two means doesn't really change all that much between these different cases. In any of the three cases, you're trying to find as much as you can about the difference between the means of two populations, mu1 and mu2. This means you either want to estimate the difference with a confidence interval, or you want to test the claim that there is no difference with a hypothesis test. But where the three cases do differ is in the exact numbers used in those estimates or tests. To see how, let's look at the difference between the sampling distributions of the means. X bar 1 minus X bar 2 is approximately normal, with mean mu1 minus mu2, and standard deviation given here. But notice in that formula for the standard deviation, we have the two population standard deviations of the two underlying original populations, sigma 1 and sigma 2. So depending on whether those values are known or not, or whether or not we assume they're equal, that'll affect exactly how we construct a confidence interval or conduct a test. They'll have an effect because the margin of error in the confidence interval and the test statistic in the hypothesis test will change. But actually, other than that, the general methodology isn't really affected. So what I'll do now is give the formulas for the margin of error in a confidence interval in all three cases and the test statistic in all three cases to highlight how the three different situations do differ. So first case, if sigma 1 and sigma 2 are known, the margin of error in the confidence interval is given here. Notice the critical value in that formula. It's a z-score. That's one of the things that will differ later on. The centre of the interval is always the difference between the two sample means, and that centre doesn't depend on what we assume or don't assume about the sigmas. And the test statistic in a test for whether there is a difference between the means is given here. Again, this test statistic is a z-score because the standard deviations are assumed to be known. If we don't assume that we know sigma 1 and sigma 2, we have to estimate them with sample standard deviations. Now this does affect the sampling distributions, so the margin of error in the confidence interval is now given here. Apart from the fact that the sigmas have been replaced with s's, the critical value is now a t-score, but actually that's all that's changed. And similarly, here is the test statistic when we don't assume anything about the sigmas. Finally, the third case, if we do assume that the two unknown standard deviations are equal, then instead of estimating them with separate sample standard deviations, we estimate them with the same pooled standard deviation. The formula for the pooled sample standard deviation is given here. So here is the margin of error for the confidence interval in this case. And here is the test statistic. The main difference is that we use the pooled standard deviation to estimate the sigmas, not separate sample standard deviations. So there are a lot of different possibilities here, and you'll get better at spotting the correct method to use as you get more practice. In the Pedisco workbook, we have a variety of questions that help you detect which situation you're in and which method to use. So right now, let's have a look at one such situation. In this question, the average incomes from two different states are being compared. We have a sample of incomes from state A and another sample of incomes from state B. We're being asked to find the 95% confidence interval for the difference between the two mean incomes. Notice that there's no information presented about the population standard deviations. When this is the case, the safest thing to do is to not assume anything about them, and so we use the separate sample standard deviations to calculate the upper and lower bounds, which I did earlier. And as we submit our answers, we see we get personalised feedback and an explanation of the question. So that was comparing populations. The key topics were dealing with two population parameters, inferences about two population proportions, and inferences about two population means.